thank you. So welcome after the break, and I hope that my presentation won't be too boring and you won't get to sleep after lunch. So today I will give you a very brief, because I don't have much time, status report on formalism causal dynamical triangulations, which is an approach to quantize gravity using rather quite traditional lattice quantum theory approach. And it was done with many people, especially Professor Jagiellonian, who was also a member of POTOR and who unfortunately died almost 2 years ago, with Regge from the Jagiellonian University, with another from Copenhagen and Nijmegen, and PhD and postdoc students, which are listed here. Okay, so just as a very short introduction, it was Einstein who noticed that probably general relativity will have to be somehow changed or improved by quantum theory. However, there is more than 100 years after the discovery of GR, but we still don't have like a complete full theory of quantum gravity. There is a number of approaches, just I list here a few of them, and today I will especially focus on these lattice quantum field theory approaches, including the DR also mentioned relativity classification. So what are the problems or challenges in quantizing gravity? So first of all, we don't have experiments, so we don't have any guidance. And also from these conceptual issues, it was shown that at least on the quantum field theory, which is based on Einstein's gravity, is non-normalizable, and also some simple extensions have problems with unitarity. So it is quite commonly believed that one has to use non-perturbative and background-independent approaches, which is quite difficult in general. And but hopefully, if we use these approaches, there is a hope that was conjectured by Stephen Weinberg that in this so-called asymptotic safety conjecture, that one can formulate a UV complete, so non-perturbatively renormalizable theory of quantum gravity, which would be predicted at all steps. So lattice approaches are in particular useful in investigating these non-perturbative regimes, and in principle then potentially can allow to check this asymptotic safety conjecture in a fully unitary, non-perturbative, background independent, and hopefully also the formalism invariant way. And actually historically there were two main approaches in the lattice QFT to quantum gravity. Actually the first one was to just formulate just more or less to use Ashoka variables, so to formulate this cage theory, to put it on the regular lattice, but unfortunately it didn't go to any interesting results, most likely because the formalism invariance was badly broken in this kind of approaches. Another group of approaches, which is also CDT, is to use the lattice itself to make it dynamical and on geometric degrees of freedom, and to work directly on the ensemble of geometries in the quantum table. And actually, in order to be able to have the continuum, to define the continuum in the lattice field theory, one should observe high order phase transitions. And potentially in such a high order phase transition, one can be able to define the continuum, which may be consistent with the theory fixed point of quantum gravity as stipulated by Weinberg. And also one, of course, would like to be able to reconstruct semiclassical gravity, so something which would be consistent with lower energy limit with GR. And it seems that in order to have these features, some notion of causality should be imposed on top of the theory, which leads to causal dynamical triangulations. They were started in 1998. It was the first article about CDT. And basically it was formulated by Jan Ambior, Jagiellonian, and Krakow, so we have almost 25 years from the start of this approach. So in general, what are the main goals of lattice VFT? So suppose we are able to formulate this theory, which has all these welcome features, and then in this theory we would like to study, if it is possible, some potentially emerging, dynamically emerging background geometry and fluctuations about this background geometry, and hopefully find some non-trivial properties of quantum spacetime at the time scale, and then maybe from these non-trivial predictions, construction phenomenology, or maybe some observational effects, most likely in cosmology or in the physics of black holes. And also possibly to unify with other with matter fields. Today I will not have time to discuss matter fields in CDT, so I will just focus on the geography. So this is my outline of my presentation. I will very briefly introduce the Causal Dynamical Triangulations. Then I will talk a little bit about the phase structure in this model, and phase transition. Just I want to remind you, we are interested to have higher order phase transition in order to be able to define the continuum. Then I will discuss what is the semi-classical limit, which is, I think, quite well defined, and how do we try to look for a continuum limit in this approach. Okay, so as already mentioned, CDT is based on the lattice quantitative theory approach, and actually it is based on the path integral quantization. Okay, so we would like to give a very precise meaning to this formal expression, which is just the integral over geometries. These are the formalisms in invariance classes of metrics. Okay, so these are just over geometries. We don't want to double count, the same geometry. We have some measure term, and we have exponent of I2 times the gravitational action. So one should very precisely define what is meant by this geometry, so which class of geometry should enter the path integral, right? What is the action which should be used, which symmetries of GR, maybe all homomorphism invariance methods should be imposed, and how to do that on the lattice. Then what is the measure there, so this is G, and of course how to compute this path integral in practice, and how to deal with quite generic divergences and possible problems with unitarity. So CDT gives very precise answers to all these questions. So first of all, let me discuss what are the geometries that we take into consideration in CDT. So in classical GR, one usually deals with smooth pseudo-Riemannian manifolds, and it is, I think, quite commonly believed that this class of geometries should be increased, so one should include not only smooth geometry, but also general continuum geometries. For example, let's take an example of the quantum mechanics of a single particle. Then in the path integral trajectory, generic path integral trajectory is nowhere differentiable, but it is continuous. Okay, so more or less the same concept should be translated into geometries or graph. So CDT makes these additional assumptions about this causal structure of spacetime. So we do assume that we sum over only we take into account only globally hyperbolic geometries, globally hyperbolic spacetimes, which can be topologically foliated into spatial slices of global cosmological time. And I have to stress here that the nature of this time foliation is not fully understood in CDT. So there are some signs that it can be just a convenient kind of gauge choice, but it may be as well that we are taking the full four-dimensional deformity symmetry. We are just left with this deformity with the spatial slices, and we have some different time direction. And for the purpose of this talk, let me assume that we do that. Right? So we have just different time direction, and we might have been clear with this assumption. And also, should we take all such geometries, or maybe should we somehow restrict them? So, for example, should we take into account all possible topologies, and so on? So CDT takes quite a minimalistic approach, so we fix the topology of each spatial slice. We assume that it cannot change in the time evolution, because such a change would most likely break causality. And we also, for practical reasons, impose time periodic boundary conditions. So far we have investigated two cases of the spatial spherical topology. This is the so-called spherical CDT, or the spatial toroidal topology, which is the so-called toroidal CDT. And actually we approximate these all geometries by triangulations, the so-called piecewise linear manifolds, which are constructed from two types of simplicial building blocks. Okay, so we just have these two building blocks like Lego blocks. Okay, we glue them together in all possible ways in order to obey these topological restrictions, okay, not to have any topological defects. And we do assume that the interior of each fourth simplex is a piece of flat Minkowski spacetime, and non-trivial geometry and curvature is encountered in the way they are glued together. And it's just, we hope that such an ensemble of geometries is dense in the whole ensemble of possible geometries, and replace the path integral by a sum of such triangulations. Okay. So what about the action and the isomorphic symmetry? So we just used simply the Einstein-Hilbert action. It can be shown that for the type of geometries for this triangulation, so for these piecewise linear manifolds which we use, it takes a very simple form of the so-called Regge's action. So Regge shown how to translate Einstein-Hilbert action into these triangulations. And actually, the non-trivial curvature is locally defined by deficit angles, which are around d-2 dimensional objects, so for the 4-dimensional case around triangles. And also, this Regge formulation uses only geometric invariants, like lengths of edges and angles, so we don't have any coordinates in the system. So from this point of view, this diffeomorphism invariance is just there, because we don't use coordinates. We just work directly on the space of geometries. With this dot, that maybe we have this preferred line foliation. And also, as we use only two types of the building blocks, this Regge action takes a very simple form for the finite triangulation. It is just a linear combination of three global numbers, so the total number of four simplices in the triangulation, the total number of one simplicity, this is one of the building blocks, the total number of vertices, and 0. And we have three coupling constants, K0, K4, and delta, which are related to the Newton's constant, the cosmological constant, and the asymmetry between space and time, which also would break this four-dimensional diffeomorphism variance might have some physical meaning. All right. So what about the measure time and computations? So we just take a trivial measure, okay? So this 1 over Ct, this Ct just counts the number of symmetries per triangulation, so we don't double count triangulations which represent the same geometry. It can be easily included in our approach. And how to do that in practice, how to compute, we use Monte Carlo simulations. So in order to use Monte Carlo simulations, we need to rotate from the Lorentzian setting to Euclidean setting. Okay? Fortunately, because of this imposed time formation, this peak rotation is well defined for each individual triangulation. Okay? So if we peak rotate, the simplices the integral of simplices become parts of the Euclidean instead of the Minkowski space. We can also rotate the action by continuing this parameter alpha from negative to positive values. Okay? And then we are just left with some statistical theory of fluctuating geometries, which enables us to numerically measure some, say, expectation values or correlation factors of observables. All right. What about divergences and unitarity? So it was shown that CDT, due to the time formation, has reflection positive and symmetric and bounded transfer matrix, which in ordinary field theories guarantees unitarity, so we hope there is no problem with unitarity. Also for final lattice size, the number of four simplices, we have no problem with divergences. And I must stress that we do not assume that space-time is discrete in any sense. Okay? So this lattice spacing which is there, this just plays role of a UV cutoff, so say momentum cutoff is of order 1 over lattice spacing, and we want to remove this cutoff in the continuum limit if it exists, and which means that we want to go with lattice spacing to 0, and with the number of simplices to infinity, in such a way that the total physical formula is fixed. Alright, so now about the results. So first of all, we discussed the phase structure and the phase transitions. Just remind you, we want to have higher order phase transitions in order to be possibly be able to define the continuum. So, okay, this is the phase diagram of the spherical and of the toroidal CDT. What is on the axis? This is delta and K0 coupling constants. Just remind you, this K0 is related roughly to 1 over G. Delta is related to this asymmetry parameter. And actually, K4 is not there on the phase diagram because we make Monte Carlo simulations with fixed lattice volume, which means that we have to fine-tune K4 to the lattice volume. Okay? So we come somehow out, this K4 is not important. And we do observe 4 completely different phases of geometry which are in this system. And actually, we also observe the phase transitions. So the phase transitions which are in blue are first order transitions, and the first transitions which are in red are higher order transitions. All right, so how to, for example, see that we have these 4 different phases? One can, for example, measure the physical free volume of spatial slices, which is well defined, okay, because we have this preferred time direction. So this is our kind of observable. And then this is just related to the number of tetrahedra which form each of these spatial slices. And when you plot these volume profiles as a function of lattice time, you see that there is a different behavior in each of the phases. Actually, in toroidal CDT, it behaves quite differently in all 4 phases. For the case of spherical CDT, there is quite a similar volume profile for this phase CP and phase CBS. However, one can, for example, track the difference between these 2 phases by measuring the effective dimension of the dynamically emerging geometry, which is observed there. So why do we talk about effective dimension? So we have these 4-dimensional objects which are forming a triangulation, but the generic triangulation is very fractal. Here we have some 2-dimensional example. In 4 dimensions, it is even more fractal. So for such fractal geometries, one can try to define some notion of effective dimension. They just cannot be embedded in the 4-dimensional space, even though they are constructed from 4-dimensional objects. And for example, one can measure the so-called Hausdorff dimension here is defined by some scaling properties of the volume profiles. So if Hausdorff dimension is 4, we should expect that the volume of the spatial slices should scale as a total volume to power 3 over 4, and the time extent of the universe should scale as total volume to power 1 over 4. And this is indeed the case in this phase CDS, which later I will call the semiclassical phase. And this is not, for example, the case in phase CB. So this is the difference. One can also measure the so-called spectral dimension, which is related to the heat kernel of the Laplace operator. Professor Shita will discuss that from the Laplace operator and then extract many things, including the effective dimension of spacetime, and also in this phase CBS for macroscopic scale, this is consistent with 4, and it is different in different phases. One can do even more. One can use completely automatic machine learning methods to distinguish between the phases. We did it recently, and we just investigated many of machine learning methods, and everything which is in blue is consistent with our previous phase transition studies. Okay? So it means that also completely automatically we can just distinguish these phases and phase transitions. All right. What about the phase transitions? So first of all, we assume that it makes sense to use traditional methods of statistical physics to distinguish between the orders of the phase transitions. It is not so clear because here we are dealing with fluctuating geometries, okay? Not with fields on the fixed geometry, but we still assume it makes sense to use these traditional methods. And these methods require to define some order parameters. I have no time to go into details, but basically these order parameters track symmetry differences between these various phases, okay? And they just change from one phase to another, and by looking at these order parameters, we can very precisely locate the position of the phase transition, and then we can use some finite size scaling analysis, compute some critical exponents, and so on and so forth, and then based on that, so these are just traditional methods using statistical physics, we can distinguish between first and second order transitions. So, for example, in spherical CDT, this transition here between phase DS and CB was found to be a higher order transition. We also, this one is also higher order. Okay. Yes, and we are especially interested in the phase transitions which are surrounding this physically interesting phase CBS, in which potentially we observe the 4-dimensional universe. And for that case, I will focus on the spherical CDT, because it seems that the phases which are bordering the toroidal CDT phase CBS are first order. There is still a hope that the continuum can be defined in these endpoints, okay? Because they may be higher order. It's quite common. These endpoints are higher order, but it is much more difficult to check, right? So let me just focus on the case of the spherical CDT. All right. So I would like now to convince you that what we observe inside this phase CBS in the spherical CDT is consistent with some semi-classical limit of gravity, of quantum gravity. I already mentioned that we have these effective dimensions, which for large enough scales are consistent with 4, so with the effectively 4-dimensional universe. Also, there is a non-trivial feature of the spectral dimension, namely, if you go with the somehow scale to lower and smaller scales, it changes from 4 to roughly 2 for very short scales. And this was actually first discovered in CDT. This is called dimensional reduction, but it is quite a generic feature which seems to appear in many approaches to quantum gravity. So maybe there is something deeper in it. And maybe based on that one can construct some phenomenology and maybe some observational effects. And if you are interested, just I refer you to the article of Stephen Cardiff about that. Okay, but just let me continue about these semi-classical features. So first of all, we have this volume profile, okay, which can be measured in numerical simulations. We can average over these, many triangulations, and then we have this average or expected volume profile. And it seems that it is really consistent with the volume profile of the regular force field, okay? And the regular force field is just classically the solution of Euclidean Einstein equations, okay? So this is the Euclidean de-Sitter universe, so this is the maximally symmetric space with positive cosmological constants, so which is obtained from four spatially homogeneous and isotropic metric. So for this kind of metric, when we have the scale factor, and this is just the line element of the regular free sphere. And one can also measure something more. Recently there was a proposal by a group of Professor Lal to define something which is called quantum Ricci curvature, which is some notion of the local curvature. I don't have much time to go into details, but starting from some scale, one observes something which seems to be also really closely resembling this constant curvature profile of the force field. And also one can introduce some homogeneity in isotropy measures. And it seems that also starting from some scale, the universe we are observing, this quantum universe, is pretty homogeneous and isotropic. Even though it is pretty small, because in the lattice, the estimated size of this universe is of order of few point max. Okay, what is even more, we can also measure quantum fluctuations of the scale factor on top of this dynamically emerging geometry. And it was shown that it agrees really well with the discretized mini-superspace action, right? So the mini-superspace action is also obtained from the Einstein-Hilbert action for the homogeneous and isotropic metric, okay? So we will just plug this metric into Einstein-Hilbert action, and the mini-superspace action here it is just parameterized by the volume, which is proportional to scale factor squared cube. And it was shown that it really well describes our data, which we measure numerically. So just to sum up this part, we're just observing something which looks very classical, okay, some classical background with superimposed quantum fluctuations, which are very well described by the mini-superspace model, which is this semi-classical unit. And it was kind of derived, okay, because we have all these geometric degrees of freedom, not only the scale factor, okay, so we don't make this assumption that the universe is homogeneous or isotropic. This is just a result, okay, which is okay. What is more? So inside this phase CDS, there is some specific scaling of the volume profile and the fluctuations profile. Just because this order dimension is 4, just I would like to draw attention to this power here. So volume profile scales as total volume power 3 over 4, and the fluctuations scale as square root of n4. Okay, and also I just defined the shape parameter, this is just somehow like this asymmetry between space and time. So in fact, we are having some elongated sphere, okay, instead of regular sphere, because just the time direction can be a little bit different than spatial directions. And this gamma is related to the fluctuations amplitude, which actually is one of the parameters of the effective action which we measure. And also by looking at this effective action and by comparing these dimensions for quantities which are observed for the continuum theory and the dimensionless quantities, so parameters which are observed from the lattice, one can show that the lattice spacing is just proportional to G, which is the Newton's constant, divided by this gamma omega squared. And actually, so what happens for a fixed point in our parameter space inside phase CDS? So for a fixed point, this gamma and omega are constant. If you also assume that the Newton constant is constant, then it means that the lattice spacing is constant and positive. Okay, so this is not the continuum ring. The lattice spacing is fixed and positive. And then if we take the n4 going to infinity limit, it also means that the relative quantity of fluctuations disappears in the large lattice limit. So it means that we recover something which is completely classical. So this is this infra relativity. So how to search for the continuum limit? I will start with a very, very simple example of the lattice side to 4 theory, where we have two dimensionless coupling constant m0 and lambda. This lambda is related to this 5-4 coupling. And one can show that there are two phases, and there is also some higher order phase transition line between the two phases. And actually, how to define this normalization group graph on such lattice? So one can just measure the renormalized coupling lambda r, which is related to some 4-point correlation function. It can be done. And we can try to follow the trajectories of fixed lambda r in the direction of decreasing lattice spacing. Okay? And hopefully, I would like to end in some higher order transition point. But it turns out that there is no such trajectories that lead to any this point, which simply means that there is no continuum limit of the 5 to the 4 lattice theory. If it led to some fixed point, one could define this continuum limit, and there are some signs going from the so-called conventional normalization group law studies, which is like the asymptotic safety, that it might be the case when practicing gravity. So how do we want to realize it in practice for CDT? So we would like to find a limit in which we go with the number of simplices of the lattice size to infinity. At the same time, we want to go with lattice spacing to 0, such that the physical formula, which is lattice constant, which means that the lattice spacing is proportional to n4 to this power. Okay? At the same time, we want to keep this shape of the universe, which is defined by this parameter omega constant, and it will define these lines of constant physics. And we also want to keep this relative quantum fluctuations constant, such that changing the lattice spacing, we investigate the same physics. One can show that it also leads to the fact that all parameters or renormalized couplings, which are in this mini-superspace action, dimensions for mini-superspace action, this continuous mini-superspace function are kept fixed. Okay? So we somehow keep this renormalized couplings fixed. Okay, so we have these two conditions, and we just parameterize this flow by n4, because lattice spacing just behaves as n4 to this power. And so we should find such lines which hopefully lead to some higher order transition point. How does it look in practice? So these are the lines of constant omega. Okay? So this is how this flow. So the flow should go around by these lines, and this is the shape of this gamma, which we would like to increase. Okay? Because it should be proportional to n4 to the power 1/4, and we want to go with n4 to infinity. So this should basically go following these lines in the direction of the decreasing lattice spacing, so this way. Okay? So basically, this is the shape of the RG flow, which we do observe from the lattice. And now there's a big question if there are any lines leading to a higher order transition point. So actually, most of these lines seem to be avoiding this phase transition, okay? And they are just, going somewhere up. But there is some collection of these flow lines which potentially may go to this higher order point. Unfortunately, at the time where this analysis was done, it was in 2014, the resolution of the data was not good enough to answer this question. So this is still an open problem. Also, the problem at that time, so this is, our conjecture that probably some of these lines may lead to really fixed point where one can define the continuum limit of our approach. But this is, as I said, still an open question. And right now we are repeating these measurements, and hopefully in some time I will be able to tell you something more about that. So just to sum up, once again, these were at least part of the goals which we wanted to achieve. And I think that we did achieve everything which is in green. So we had some unitary formulation and non-perturbative and background independent of quantum gravity. We still don't know if it is really complete because we don't know if this continuum limit exists or not. In this approach, we can study this dynamically emerging spacetime, which is we superimpose quantum calculations. We have some non-trivial signatures of quantum gravity. This is this dimensional reduction. And also we have the semiclassical behavior in one of the phases, and we think we know how to define the Archie's law and how to search for the continuum limit, but we still are not sure if this continuum exists or not. So this is the end of my talk. Thank you very much.
Time for short questions.
So you said at the beginning that CDT can be seen as a method to verify the asymptotic safety conjecture, as far as I understand. Even if this conjecture was false, CDT could still tell us something like quantum.
Yeah, so I mean, the main goal of quantum gravity is, as I understand, to formulate some UV complete, okay? So, non-particular theory, non-resolute theory. But if there is no continuum limit, CDT can be viewed just as some effective field theory of quantum gravity, which is valid up to some finite scale, of order of the Planck scale, with potentially some non-trivial observational effects, which can be done. Okay, so this will be like kind of the tool, like for example, lattice QCD for quantum kernel dynamics. So this could be like a lattice kind of tool to investigate some properties of quantum gravity in an effective approach.
And how advanced are you in coupling matter?
Okay, so I didn't have time to mention that today, but what we did couple some scalar fields to CDT, and depending on the boundary conditions we impose on these scalar fields, they might either have no too much effect on the geometry, but for some specific boundary conditions, they do have some great impact on the geometry, leading to some new phase transition and so on. So it was for the scalar fields. We also did some measurements for point particles, so mass lines. And there was also some other group which did include gauge fields, I think at least in 3 dimensions. I'm not sure if in 4 dimensions also as well. So it can be, basically it can be done.
But is it, in zeroth order approximation, is it clear how to do it? Or each time you have to solve some unsolved problems?
I would say that rather the second sentence is true. So, for example, it depends on which field we want to. So, for some kind of matter fields, it's easier. For some, it is more difficult. For example, for this point particles, there were a lot of unsolved problems. For example, how this mass line should go, can it come back in time direction or not? We have to make some choices. Okay, so it is also somehow approach dependent.
Okay, so let's find out